Alright, welcome to Unit 7. This one's on acids and bases. So we're going to start by defining what acids and bases actually are. You've probably heard the terms many times before, probably know a little bit about acids, not a whole lot about bases. So after this video, you'll know quite a bit more. So some common ways to distinguish acids and bases are by their properties. We'll get to their definitions in a bit, but most of the time, you're going to think of them as you're going to look at something or see what it does. You're going to care more about its properties rather than the actual chemical definition. So we're going to start with those. Acids taste sour and bases taste bitter. Now, this does not mean that every bitter thing is a base and every sour thing is an acid. However, many things that are sour have some acidic component to them, and many things that are bitter have some basic component to them. Common acids are, lemon juice. Or just about lemons. Actually, most citrus. They've got what's called citric acid in them. Let me think. Vinegar, that's another one. And a lot of common things that you've got at home probably have some kind of acid in them. Bases, very common example are soap or cleaners. Tend to be basic. So there's many more, and we'll talk a little bit more about them throughout the unit. But again, acids taste sour and bases are bitter. Okay, acids tend to react with metals to produce hydrogen gas. Now, bases don't always, but for example, a very common acid lab is you take a ribbon, if you will, of magnesium metal, kind of spiral it and put it in some kind of a tube, and then you pour some acid on top of it. And what happens is it basically starts foaming up and bubbling, and you produce all these bubbles. Almost any time, if you've ever poured any kind of acid or something, or in our class I'll probably do some, you pour it on stuff and it starts fizzing, that's pretty much hydrogen gas. Bases, some of them produce some types of gas, but they're not consistently doing anything, so we really don't care. But pretty much every acid will produce hydrogen gas when it reacts with a metal. Bases tend to feel slippery or slimy. As with the previous one, acids do commonly have characteristics with them. It's just they're not quite as reliable as the sliminess or slipperiness of bases. But again, go back to soap. Soap tends to feel slimy, tends to feel slippery. It's actually very known for that. That's a very, very common base. But there you go. Bases are slippery and slimy. Again, there's no predictable thing for acids, so we just don't care. And again, with a very concentrated acid or base, you won't really feel much. It'll kind of eat through your hands, so be very careful with acids and bases. But again, soap is a very non-concentrated base. We'll talk more about that a bit later. Acids turn indicators red, whereas bases turn indicators. Yeah, indicators, not bases. So, two common ways of testing whether compounds or acids or bases are we use what are called litmus papers. We'll talk more about this in a bit. But there's two main types. There's red litmus papers and blue litmus paper. And basically, acids will turn the red ones red, so you won't really notice anything. But it'll turn the bases blue, like if I put a little drop on there. And bases will turn the red ones blue. So there's many common ways that we do things. Just a lot of the indicators, typically, acids tend to be a little bit reddish, bases blue. The most common ones when we're dealing with this are the litmus paper. And to be honest, they're not really that useful because all it tells you is whether it's an acid or a base. It doesn't tell you how strong it is, but it's useful at some points. Again, I'll show you those in a bit. Okay, so now we've talked about properties. Now we're going to go to definitions. So there's three main definitions of acids, and they're all basically true. We'll focus on one for most of our time, but they're all actually true. Just one's more common. So the first definition is by Arrhenius. And according to Arrhenius, acids are compounds that increase the hydrogen ion, which is typically just H+, concentration, when we dissolve in water, and bases increase the hydroxide. So acids deal with the concentration of hydrogen ions, and bases deal with the concentration of hydroxide ions. So acids will increase hydrogen concentration and bases hydroxide. This does not mean that they'll produce hydrogen or produce hydroxide. A very common way the bases react is they actually take hydrogen from water, which leaves over, or remains, hydroxide. So technically they kind of make hydroxide, but they don't really come with it. Arrhenius is not the most common definition, but anything that increases hydrogen can be considered an acid. Anything that increases hydroxide can be considered a base. Bronsted-Lowry's is our most common definition. And these are acids that acids are compounds that donate a hydrogen ion. Commonly, we're going to call that a proton. Hydrogen ions typically have one proton and one electron. H plus means it gave away the electron. So H plus means we lose one electron, which means instead of having one proton and one electron, now we have one proton and 0 electrons. So we typically just call it a proton. And bases accept hydrogens. So typically what you'll see is that acids will give a proton to a base. So most of the time things that have an H at the beginning of their name will be an acid. Most things that end with an OH at the end will be a base. And then typically these two will form water when acids and bases react. We'll talk more about that later, but Bronsted-Lowry is our most common one. Our last one though is the Lewis definition. And according to Lewis, an acid is a substance that can accept a pair of electrons to form a covalent bond. And a base is a substance that can donate a pair of electrons to form a covalent bond. This is actually really, really, really uncommon definition. I'm still teaching to you. It's important for you to know, but you're not going to use it a whole lot. Bronsted-Lowry is a little bit more useful. But we'll talk more in an example. It's just when you're actually dealing with transferring pairs, you can look into how molecules are formed. And typically an acid is a compound that is going to start basically formed and the base will attach to it. It's kind of weird. But nonetheless, that's the Lewis definition. And in a little bit, I'll show you some more examples. Last main thing. We've talked about properties of acids and bases. We've talked about definitions of acids and bases. Now we need to talk about conjugate acids and bases. Not too hard though. Conjugate acid is basically the ion or molecule formed when a base gains a hydrogen ion. So, a while ago I showed you, not a while ago, like the last slide, I showed you typically acids give bases protons. What's left over when an acid gives a proton, we're going to call the conjugate base. And what's left over when the base gains that proton, we're going to call the conjugate acid. So conjugate acid is when a base gains a hydrogen ion, or sometimes we call it a proton. Okay. And a conjugate base is when an acid loses a hydrogen ion. So a very common acid is HCl, hydrochloric acid. And when it reacts, it basically gives away that hydrogen, and you're left with chloride. This, we would call, is the conjugate base of that acid, because it's basically that acid without an H. It's really all it comes down to. So, conjugate acids are when bases are when bases gain a proton. Conjugate bases are when acids lose a proton. Most of the time, they'll look basically identical, except for one will have an H and one won't. That's kind of what it comes down to. And a conjugate acid-base pair consists of two ions or molecules, again, sorry, I just said that, related by the loss or gain of one hydrogen ion. So again, HCl and Cl minus would be considered a conjugate acid-base pair. We would call this the acid and this the conjugate base. There you go. And for the future, the hydronium ion, this, is basically the same as a hydrogen ion. It's basically, most of these things are done in aqueous solutions, meaning there's water. Hydronium is basically what happens when you put hydrogen in water. But since we know it's in water, we sometimes just write hydrogen. So what that means is that the concentration of hydrogen is the same as the concentration of hydronium. So if you ever see hydronium or H3O plus, know that it's basically just talking about hydrogen. All right, let's do some. So we are going to identify each compound as an acid, base, conjugate acid, or conjugate base. I'm going to do the first. Actually, I lied. I'm going to let you guys try these, and then I'll come back and show you how to do them. So take a few minutes. Yeah, I will say it does not matter what side you label acids base on, but one of your sides will be acid and base, and the other will be conjugate acid, conjugate base. So you won't have an acid and a conjugate base on the same side, or an acid and a conjugate acid. By convention, typically the left side is acids and bases, the right are the conjugates. So with that, take a few minutes and come on back. Okay, welcome back. Let's start working on this. So when we look at NH3, typically what we're doing is we're going to find whatever compound looks like this on the products. Well, NH3 doesn't really look like OH minus. It looks a lot like NH4 plus. So we're going to assume that these are going to form some conjugate acid-base pair. We just got to figure out which one's the acid and which one's the base, basically. So this has 3 hydrogens. This has 4. That means that from here to here, we gained a hydrogen. That means that this is going to be our base, because bases accept protons, and this will be our conjugate acid. Now, by process of elimination, that means acid conjugate base, but let's work through it. We have H2O, and we have OH minus. A very common useful technique is to think of water as HOH, because then you think of it as hydrogen and hydroxide. You don't have to, but it helps in this case, because then you can see that this is just OH minus with an H. So we have 2, we have 1 over there. So 2, 1. That means that this will be our acid, and this will be our conjugate base, because this is basically our original acid after it lost a hydrogen. Alright, let's try the next one. We have HCl goes with Cl minus. That's our acid. It's our conjugate base because we lost an H. We have 2 hydrogens. We have 3 hydrogens. That means we gained an H. So that means water is going to act as our base. And hydronium is going to act as our conjugate acid. Hopefully you noticed that water has actually been both acid and a base up here. We'll talk about compounds that can do that. They're called it's either amphoteric, amphiprotic. There's one. I'm sorry, I always mix those words up. We'll talk about that later, though. Lastly, acid, base. Now, here's where it gets a bit weird. Because I just pointed out to you that water can actually be acid or a base. So, put simply, in situations like this, where this chlorine part's our conjugate base, and the sodium part is our conjugate acid, it's actually going to be neither. So, I'm sorry, I actually gave this to you. So there are 2 options. You can call that your acid and call that your base. Call that your base, call that your acid. What you'll eventually learn, and of course I totally forgot to tell you on this, is we're going to call this water. We're going to call this our salt. So, to be honest, I thought I didn't put that on here. Oh well. Nonetheless, though, if you can do these, that's all you need to know. We will cover these later. So again, acid, base, conjugate. Thanks for watching.